Hello, I am Naveen Kumar Echan, Assistant Professor, Department of ECE, STMIT, Ujjiri. The topic of today's session is Linearity Property of Fourier Transform. The following textbooks are referred to prepare the presentation. Linearity Property. An operator is said to be linear if it satisfies principle of superposition and principle of homogeneity. An operator fails to satisfy either principle of superposition or principle of homogeneity is said to be nonlinear in nature. The operator of interest is Fourier transform relation. In order to write the linearity property for Fourier transform relation, let us consider two time domain signals x of t and y of t with Fourier transforms x of j omega and y of j omega respectively. The first relationship represents x of t and x of j omega are Fourier transform pairs. The second relation says y of t and y of j omega are Fourier transform pairs. Then the linearity property can be written as the Fourier transform of a times of x of t plus b times of y of t is a times of x of j omega plus b times of y of j omega. By observing the linearity property relation of Fourier transform, we can say like the left hand side of the relation says like the time domain signals we have taken into consideration are x of t and y of t. First, scale those time signals by factors a and b respectively, then add the scaled signals and determine the Fourier transform of the sum signal. Similarly, the right hand side of the relation represents, so first obtain the individual response. The individual response is Fourier transform of the signals x of t and y of t, means x of j omega and y of j omega. Scale x of j omega by a and y of j omega by b, then add the scale response. Like in the if right hand side and left hand side are one and the same, we can say the operator Fourier transform relation is linear in nature. What we are verifying here is overall response is equal to sum of individual response for the operator of interest. Now, like if you observe the left hand side of the relation and right hand side of the relation, we are considering three important operations. One is addition, scaling, then Fourier transform application. So what we are doing here is we are changing the order of the operation. Even after changing the order of the operations, like if we are getting the same result, then the Fourier transform relation, the operator is said to be linear in nature. Now let us prove this relation. In order to prove the relation, let us consider a times of x of t plus b times of y of t as h of t. Then for the time domain signal h of t, its Fourier transform will be h of j omega. H of j omega can be written as h of j omega equal to integral t from minus infinity to plus infinity h of t into e power minus j omega t dt. Substitute h of t in the integral equation. After substituting h of t, the integral equation looks like h of j omega equal to integral t from minus infinity to plus infinity a times of x of t plus b times of y of t times of e power minus j omega t dt. We all know that the integration function is linear in nature. Let us take an example. Integration of a1 f1 of x plus a2 f2 of x can be written as a1 times integration of f1 of x dx plus a2 times integration of f2 of x dx. f1 of x here is x of t into e power minus j omega t. f2 of x is y of t into e power minus j omega t. Now this relation can be written as h of j omega equal to a is scalar, we can take outside the integral, a times of integral t from minus infinity to plus infinity x of t into e power minus j omega t dt plus b into integral t from minus infinity to plus infinity y of t into e power minus j omega t dt. Now observe the integral equations. We have a product of a time domain signal and a complex sinusoid inside the integral. That represents a Fourier transform relation, right? The first integral represents Fourier transform relation of the signal x of t, which can be written as x of j omega. The second integral equation represents Fourier transform relation of the signal y of t, which can be written as y of j omega. So we can write h of j omega as a times of x of j omega plus b times of y of j omega, which is the required proof. So to have a better understanding of linearity property, let us solve a problem on linearity property of Fourier transform. Let us consider problem on linearity property. The problem statement will be like, so use the linearity property to determine the Fourier transform of x of t equal to 2 times of e power minus t u of t minus 3 times of e power minus 2t u of t. Now how to solve this problem is, let us consider the input. Now we can write x of t as a times of x1 of t plus b times of x2 of t. Observe the input. It's a combination of two time domain signals. One is e power minus t u of t and the second one is e power minus 2t u of t. Now by comparing, I can write down the value of a, b, x1, x2. A is equal to 2, b equal to minus 3, x1 of t equal to e power minus t u of t, x2 of t equal to e power minus 2t u of t. Now use the linearity property relation of Fourier transform. So the linearity property is a times of x1 of t plus b times of x2 of t. Fourier transform is a times of x1 of j omega plus b times of x2 of j omega. First obtain the individual Fourier transform response like x1 of j omega and x2 of j omega. Put it in the form of a times of x1 of j omega plus b times of x2 of j omega. So by that we can determine the Fourier transform of the signal x of t. x1 of j omega and can be determined by the Fourier transform relation x1 of j omega equal to integral t from minus infinity to plus infinity x1 of t into e power minus j omega t dt. x1 of t is e power minus t into u of t. Now substitute x1 of t in the integral equation. So the Fourier transform response x1 of j omega is equal to integral t from minus infinity to plus infinity e power minus t into u of t e power minus j omega t dt. Now we can update the limits of the integral by considering step function. The step function is equal to 1, means it is true for all t greater than or equal to 0, and it is 0 for t less than 0, means for a minus infinity to 0 the step function will be 0, and 0 to infinity, for t ranges from 0 to infinity, step function will be 1. So by the characteristics of step function, we can update the limits of the integral to 0 to infinity, from minus infinity to plus infinity. x1 of j omega becomes integral 0 to infinity e power minus t e power minus j omega t dt. For this range of time 0 to infinity, the u of t value is equal to 1. Now on both the exponentials, t is common, and even we can take minus sign as common, like it looks like e power minus of 1 plus j omega times of t. Now what we have is like integration of e power ax dx. Integration of e power ax dx is e power ax by a. What is a here? A here is minus of 1 plus j omega, and x is t. Now after performing integration, we have the result as e power minus 1 plus j omega times of t divided by minus 1 plus j omega. We have to substitute the limits. The limits are 0 to infinity. Upper limit is, after substituting the limit, upper limit is infinity and the lower limit is 0. E power minus infinity. E power minus infinity is 0 and e power 0 is 1. So x1 of j omega becomes minus 1 divided by 1 plus j omega times of 0 minus 1. So I can write down x1 of j omega as 1 divided by 1 plus j omega. One of the individual response is obtained. Then we have to get the another individual response, that is x2 of j omega, which is Fourier transform of x2 of t. Now this is the relation. Now what is x2 of t? E power minus 2t times of u of t. Substitute x2 of t in the integral equation. After substituting x2 of t, the integral equation looks like x2 of j omega is equal to integral t from minus infinity to plus infinity e power minus 2t into u of t e power minus j omega t dt. Because of step function, the limits of the integral can be updated to 0 to infinity, from minus infinity to plus infinity. Step function is 1 for t ranges from 0 to infinity. So integral 0 to infinity e power minus 2t e power minus j omega t dt. Here again t is common in both the exponentials, so the expression can be written as, integral equation can be written as integral 0 to infinity e power minus 2 plus j omega times of t dt. Again it is of the form integration of e power ax dx, which will be e power ax by a. Now the value of a here is minus of 2 plus j omega and x is t. Now after performing integration, it looks like e power minus 2 plus j omega into t divided by minus 2 plus j omega. We have to substitute the limits, where the upper limit is infinity and the lower limit is 0. Upper limit minus lower limit. By doing so, we will get the relation as minus 1 divided by 2 plus j omega e power minus 2 plus j omega times of infinity minus e power 0. E power minus infinity is 0, e power 0 is 1. Now we will get the result as x2 of j omega equal to minus 1 divided by 2 plus j omega into 0 minus 1. So finally 1 divided by 2 plus j omega. We have obtained the second individual response. Then scale the individual response by the scalar's value, then add the scale response. That is the final answer. That is the Fourier transform for the signal x of t. So how to do that? See, this is Fourier transform relation which we have taken into consideration. Now like x of j omega is Fourier transform of x of t, which is a times of x1 of j omega plus b times of x2 of j omega, where the value of a equal to 2 and b equal to minus 3. x1 of j omega is 1 divided by 1 plus j omega and x2 of j omega is 1 divided by 2 plus j omega. The final answer is highlighted in red color. So similarly, like any combination of signals, like to solve for linearity, to solve for Fourier transform, we can make use of linearity property. Here in the example we have taken combination of 2. The same property can be applied to solve combination of 3, combination of 4, or combination of n. Obtain the individual responses, that is Fourier transforms, then scale the Fourier transform by scalars, then add the scale response. That will be the Fourier transform for the signal which is a combination of many continuous time signals. Thank you.